Recording's rolling. It is Thursday, September 25th. I want to do as many textbook puzzles as I can with you guys today. So I think I handed you guys the page the other day. It looks like this. Here, so if you didn't get one or something, here, I got some extras right there. That's right there. Okay, so forces. Now, you guys are my only honors class. In my AP class, they have a different textbook. What we were able to do is like some warm-up questions, some basic Newton's second law of motion. And then I was looking through trying to find some questions that look kind of like your guys' last couple or last few days. Like you guys did some Atwoods, you guys did some friction. Right? So found some like of course this is their book. And same thing with you guys. I'm going to do the first few with you guys, which is just some basic Newton's second law warm up. And then I went through and highlighted some that look like the lab. So I have some here that look like friction or they involve friction. And then on the back, there are just a couple of Atwoods. I really only found a couple of Atwoods in your book. So yeah, we'll do some of those. I might set up some of my own. Let's see how this paces out. All right. All right. So forces here. Yeah, let's do these first few. I think are the big ones. Okay, number 9, a battery-powered lawnmower has a mass of 48 kilograms. Okay. You guys remember kilograms is how much mass, right? So just like this, even if it was floating around in space, it still has that same amount of inertia, same amount of mass. If the net external force on the lawnmower, including your push and any resistance, is 40.5 newtons, then what is the lawnmower's acceleration? So I wanted to draw a picture so you guys can see the full context of what we're talking about. This is number 9, forces. We're over here. So we're talking about pushing a lawnmower around. Right? So maybe you have a ground. Right? Maybe you have like this lawnmower. Maybe it looks something like this. For example, something like that. It's got like little wheels on it or something. Right. So it could have a lot of different forces going on with it. So to give you guys maybe a more realistic kind of picture, I think this lawnmower probably has some weight. Call it mg for weight. Um, maybe here I'll keep this kind of simple. Suppose there's no other vertical forces other than normal force. Okay, and maybe you're pushing it forwards with some applied force. I'll call it F applied. Okay. And maybe there's some friction force that's partially resisting that. Call it F sub FR. Okay. Okay. That could probably be a pretty basic, straightforward example. Now, realistically, maybe you're kind of pushing down and forward, but I'm not going to even worry about that. Let's just say you're only pushing straight forward and the friction is straight backward. Right, so that could be right. That could be a free body diagram, FBD, free body diagram for pushing the lawnmower on number 9. Okay? Now, in this case, do you guys think the weight and the normal force cancel out? Right, so not worry about this much, right? And maybe you're pushing forwards more than the friction is resisting. Do you guys see how I have a net force in the horizontal direction? One, these horizontal force is bigger than the other. Okay, so I could say that F net in this case is F applied. This is like you're pushing forward minus the friction force that's resisting that motion backwards. Right? So the forward force minus backward force, the net force. Right? And even everything I've drawn so far is just trying to give you guys the full context of the big picture of something that's more realistic what's going on. But now is actually where we cut to the numbers that they gave you. So they said the net force is 40.5 newtons. So suppose after you consider this, right, you've already taken care of that. It all comes out to only 40.5 newtons. Right? Okay. So if we pick up from that point, and I could bring in Newton's second law of motion. We get this phone call. Pause this. All right, we're back recording. And so here's Newton's second law of motion. It tells you how something accelerates. Right. So from this dynamics perspective, it's net force acting on the mass. You just take the red pass there. All right. Yeah, thanks. Right. So you got some mass here. Right. You put some force on it. Right. Maybe there's a bunch of forces, but they all right, kind of conspire to create a net force. Right. And so let's look at here. What's the acceleration? Equals net force on mass. Right? That's Newton's second law of motion right there. I'll label that Newton's second law of motion. Okay. Right. So the net force is 40.5 newtons. That goes right there. 40.5 newtons. Okay. And the mass they told you was 48 kilograms. So that goes right here. 48 kilograms. So you got so many newtons of force acting on so many kilograms of mass. Right? Guess that. It divides up. That's 40.5 newtons on 48 kilograms. I'm looking at 0.84, and then there's a bunch of numbers, but I'll just cut it off at some point. A little rounding. Meters per second squared. Okay. So this lawnmower, according to how I drew this diagram, would be speeding up as it's moving forward. It's picking up speed at that rate. So every second is picking up 0.84 meters per second. Oh, 0.84 meters per second squared. Is that it? All right, so you guys good on the lawnmower? Let's get back. So it's just Newton's second law of motion, net force on mass. They gave you the net force, they gave you the mass, divide them, boom, done. That's it. Acceleration.
So that's their answer?
Yeah, that's the whole thing. That's the whole thing.
What does that say? 0.84?
Yeah. In fact, really all you had to do was just that bit right there. Right? Like if you did that, that would really be everything. Okay. So it gave you guys an additional diagram, sort of like lead into it. Like that could have given you a wider picture. Right. Number 10. A soccer ball is kicked with a force of 28 newtons. Number 10. Right. Force is 28 newtons. And the ball accelerates at 62.2 meters per second squared. So the question is, what's the mass? Right. Now, the way we just applied the second law is we said acceleration is net force on mass. But oftentimes you see this in a non-fraction form as force, and it's really the net force, equals mass times acceleration, like that. Okay? Now, I guess you could overcomplicate this by considering, well, what about the weight on the ball? And what about the, like any other forces on the ball? But we're just going to use the applied, or like the kicking force. We'll just call it the net force. We'll say that's mainly what matters here. So I got 28 newtons of force acting on some soccer ball. There's probably a standard size of a soccer ball. Like I bet if you Googled the mass of a soccer ball, it'd probably tell you something pretty close to whatever it is, I would imagine. And then this acceleration goes in right here. So 62.2 meters per second squared. Right? So you guys can solve for mass, right? Just divide both sides by the acceleration. So the mass, therefore, is 28 newtons, or 62.2 meters per second squared. Okay, 28 over 62.2. Okay. So I'm getting mass of soccer ball equals 0.45 kilograms. Okay. I think that seems about right? So that's almost half a kilogram, isn't it? Right? This lab mass is half a kilogram. So does a soccer ball weigh just a little bit less than this? Yeah, I can see that. I'm about right. About right. You guys ready for the next one? Okay. Yeah, so all we've done is number 9 and number 10 for the first one page, and they're both just Newton's second law of motion. They just relate three variables: the net force, the mass, and the acceleration. So acceleration is net force on mass. Right? So how much does something accelerate? Well, the more you push on it, the more it accelerates. The more the mass, the less it would accelerate, because inertia is trying to prevent motion or prevent change in motion. You can rearrange that and make that F equals ma. Right? If you have any two of those variables, you can solve for the third. Right? That's all. Right. All right. All right, let's go. This next one's interesting. Here, just read this. Number 14. Look at number 14 right here. Develop and use model. Draw a model of the push force between two skaters. And well, space the I pulled this out of the book somewhere. Maybe they had a space for you guys. Okay. How do the sizes of the forces experienced by the two skaters compare? What happens if one person pushes harder? We have to come up with a picture for this. So number 14 here. Suppose they got this guy's on maybe rollerblades. This guy be on little rollerblades right here. Right, maybe it's a skater. And then maybe he has a friend right here who's also on roller skates right here. Right, and maybe they're pushing away from each other. Like probably something like that, right? They push away. Okay, so if I draw a complete free body diagram, F, B, D, for each skater, maybe call this guy like skater A, call this guy skater B. Yeah. Maybe got Alan and Bob going on. Okay. So they each got a center mass, probably right about their belly button, about where your center mass is. Okay. They each have a weight. Let's make them different weights. How about that? That'd be kind of interesting, right? Okay. What if Alan Here, I'll give you guys mass of Allen is like 40 kilograms. Let's have the mass of Bob be like 30 kilograms. Okay. Guys, if Allen has a mass of 40 kilograms, how much does he weigh? Earth gravity is about 10 meters per second squared, isn't it? So wouldn't his weight be like 400 newtons? Isn't that true? 400 newtons. Okay. And so what normal force would be holding him up from the ground if the ground was just a flat ground? Yeah, 400 newtons. So the normal force is 400 newtons. Okay. And then what about Bob? Bob has a mass of only 30 kilograms. So what's his weight? Yeah, 300 newtons. Okay. And would the force holding him up from the ground, normal force, be also 300 newtons to balance that out? Okay. Now that's before they're even pushing. That's just them like standing there at rest. Okay. Now they're gonna push away from each other. Okay. So from the perspective of Alan, does Alan feel like Bob is pushing him to the left? Right? Alan says, feels like you're pushing me this way. Okay, some force. This is the force. Well, I'll say maybe Bob relative to Alan, something like that. And then there's opposite force this way, because doesn't Bob at the same time feel like Alan's pushing him to the right? Force of Alan on Bob, something like that. Okay. So the again, I gave you guys extra details because the book maybe doesn't really mention anything about their masses at all, and doesn't want you to do necessarily the force, the normal force. We did all that, so give you guys a more complete picture of what's going on. Okay? All the book is asking is what we're addressing right now is how do these two forces compare? So which force is bigger? Is the force of Bob on Alan bigger, or is the force of Alan on Bob bigger, or are they the same? Let me see. Show of hands. How many guys think that the force of Bob on Alan is bigger? Who says the force of Alan on Bob is bigger? Who says they're the same force? Ah, they are the same force. Like, isn't that a law of motion? I'm going to find it. Ah, it's right here. Is that Newton's third law of motion right here? Newton's third law of motion? Yeah. So two interacting objects, the forces are always equal and opposite. Yeah. It doesn't matter that they're different sizes or masses or none of that matters. Or even if they push harder or less hard or whatever. Okay. Now, guys, are they going to accelerate the same or they accelerate differently? They do accelerate differently. Guys, who accelerates more? Big Alan or Little Bob? Little Bob, because he has less mass. That's a second law question. So it's the same force. Okay, suppose here I'll make up something. Suppose like 100 newtons. Okay, so now that would have to be the same 100 newtons. Okay, so how much does Alan accelerate? Acceleration of Alan, wouldn't that be 100 newton force on 40 kilograms? Would be is that 2.5 meters per second squared to the left? Okay, and what's the acceleration of Bob? Well, it's the same force, opposite direction, on 30 kilograms. Ooh, could that be like 3.33 meters per second squared? And that would be to the right, because opposite direction, like equal and opposite. Right? We have equal and opposite forces, but the accelerations you have to divide by the mass of. Okay, so yeah, the smaller guy always accelerates more, but the forces are always the same. Okay. All right, you guys good there? All right, so that's the warm-ups. Let's do. Right, let's jump into some of these other questions. Right, so I'll highlight some of these that look like friction type questions. How about here? Let's do 23. Right, so have a 23. Right, 23. Two friends. Here, I should keep track of what we're doing. So we did 9, 10, 14. We're doing 23 right now. Okay, do some more of these later. Are pushing an 18-kilogram crate across the floor. One of them applies a force 75 newtons to the left, and the crate moves at a constant speed. What force must the other person be applying, and in what direction? Oh, guys, who knows what is the answer to this question? You might not even need to write anything on paper. What's the answer?
Right, 75.
Right, 75 newtons. How did you know it has to be right 75 newtons? Exactly. Yeah, because of equilibrium specifically. Okay. Now, this is not a Newton's third law question because we got two friends and a crate. So now we got one friend in a crate and the other friend in a crate. Right, we've got three different objects going on. Okay. So they could be pushing at different forces. That could be okay. In this case, they are pressing with the same force because of constant speed. Okay. So force to the left, force to the right, cancel out. Okay, so there's zero net force, and that allows for constant velocity. That reminds me a lot of. Actually, I do have a picture that looks a lot like that. Your last few days. You guys did this one, right? Okay, this could be here. This could be the crate in question. Maybe it's got to wait in a normal force. Okay, that's fine. Okay, maybe one foot is pushing to the right, the other pushes to the left. But as long as those forces cancel out, then the crate either would be at rest as possible, or it could be sliding at constant velocity. Okay. All right. Let's jump over to number 47 right here. 47. Look this one up. Right, and then okay, well, we'll see what 47. A team of dogs is pulling a person in a sled in the snow. The dogs are attached by a harness that is parallel to the ground. Okay. Okay, so they're pulling straight horizontal, parallel to the ground. The combined mass of the person and sled is 62.5 kilograms. The coefficient of kinetic friction is 0.19, and the harness tension is 180 newtons. Determine the sled's acceleration. All right, so you guys got that? You have this paper in front of you, even better, because we're going to move this and start writing some stuff down. All right, let's get a picture going. Okay. So we got some kind of sled going on. This is for number 47. That person in the sled, real cartoony type version here. And so we got some, see, sled dogs pulling to the right. Let's draw a little sled dog right here. Give a little dog tail. Right, he's just pulling straight here. And this is all across the snow, and the snow is just like straight horizontal. So pretty much that's going on. Right? Pretty much that. Okay. Okay, they gave you, I'll write some givens here. Given combined mass of person's sled is 62.5, right? So mass is 62.5 kilograms. They gave you that. They gave you the coefficient of kinetic friction between the sled and the ground as 0.19. They threw in another digit for that matter, if that matters. The harness tension is 180 newtons, so I call it F sub T, like a tension force, right? Because tension would be a force, right? It's in newtons, so that's definitely a force. 180 newtons. Right. I'll throw in one more factor because there's one more thing that does matter that they did not tell you that might be implied. What other variable also is important to be able to answer this question? How about this? Guys, if this was on the moon, do you think on the moon this might possibly move a little differently? Yeah, so maybe a different gravitational field. Okay, so let's call a gravity field an even 10 meters per second squared. Okay, okay. Yeah, and then those will be the starting values right there. Okay. Let's do a complete free body diagram, FBD, free body diagram on this person sled system right here. Okay. So called person sled, which combines 62.5 kilograms mass. Okay. Right, let's get some forces. Because what force is pulling straight down? Yeah, gravity. Okay, so weight, mg. Can we just come up with a number for that? 62.5 times 10. That would be what? 625 newtons, wouldn't it be? Right? So it's 625 newtons straight down. Now, this is on a level surface, and the sled dog is pulling, but only horizontally, nothing to do with vertical. Which means that the normal force must be how much? Yeah, 625 newtons also. Aha. Yeah. Right, so looking a lot like your guys' friction lab the other day. Now, this will be a little different than your friction lab in the sense that there is some acceleration. That was the question, right? Okay, so find acceleration. Okay, I need to label two more forces. So there's a force pulling to the right of how much? Isn't it the tension in this string, this rope right here? 180 newtons. Okay. Okay, so I'll put that at the center of mass. Okay. If I draw it a scale, it's what 180, that's almost 200. That's not quite a third of this force. So if it's to scale, this should be less than a third of either one of these forces. So I'll call it a tension force, and that is 180 newtons. Right? Okay. Okay. Now, one more force. Is what's one more force I need? Friction force. And which way is that point? To the left. Right. Now, this one, how long should I make it? Okay, it's 0.19. Is that like 19%? That's almost 20%, which would be like 1/5. Okay, it's 1/5 of what? 1/5 of what? And oh, where's my friction? Oh, it's right here, right here, right here. Right, right. Guys, here's the formula we need. Here's the connection. Okay. So the value of the friction force, like this magnitude, is equal to the coefficient of friction times the normal force. You guys see that? Okay. So that's about to tell us how long we need to make this friction force to the left. Coefficient of friction times the normal force. Plus F sub FR. Right. Yeah, I'll do a little math over here. Still a little math. Okay. So the friction force is equal to the coefficient of friction times the normal force. Okay. And we know what these values are. So coefficient of friction, that's this right here. That's 0.19. So 0.19. That's what I'm thinking about. 19%, like almost 20%. Of the normal force, which we determined already is 625 newtons. Right here. Right. 625 newtons. Is that true? Right. Now what does that come out to? So what's 0.19 times 625? That's 118.75. Friction force, if you want to round, maybe 119. I'll leave those digits. 118.75 newtons. That's way too precise, but just to really make the notes clear. Okay, so this friction force is equal to 118.75 newtons. Right, just like that. Or 119 newtons about. Okay. Again, if your picture's to scale, that friction force should be about 19% of that normal force. Got it pretty close. Right, you guys think we're close? All right, so do a pause and recap so far. Okay, so they gave you the mass, the coefficient of friction between the sled and the snow, the tension that the sled dogs are pulling, okay? And it's implied that you're allowed to know gravity field, and that also ends up being important. The question is, what's the acceleration? Now, this is eventually going to feed into Newton's second law of motion. Acceleration is net force on mass. Okay? But you can't solve that until you know what the net force is. And it's really nice to have a free body diagram so you can really check off all the forces. Right? So there are four forces: the weight and the normal force vertically, cancel. Okay. Okay. The forward force is the sled dog tension, right? So 180 newtons. And the resisting force we just found by going through friction force is coefficient of friction times normal force, coefficient of friction, bing, normal force, bing, put it together, you get bing right there. Everybody good? Okay. So now we can finally go over to Newton's second law of motion and figure out how much does this whole system accelerate. So acceleration is the big old fraction right here. Net force. Guys, what would the net force be, or how could I find it? What do you think? What would the net force be on this guy? Isn't the dog pulling to the right and the friction's pulling to the left?
Maybe 118.
Exactly. Yeah, 180 newtons to the right minus 118 newtons to the left. Yeah, there's your net force. Okay, that net force is acting on how much mass? 62.5 kilograms. So the guy plus the sled, that's it. There's the net force. There's the mass. Divide it out. I'll tell you exactly how much that accelerates. So let's do 180 this way. Okay, so make sure you can correctly plug that in the calculator also. You're not like this in parentheses or anything like that. I'm getting 0.98. And what's the unit? Guys, that's 0.98 what? Meters per second squared. Oh yeah, meters per second squared. Because newtons over kilogram, right? Or I mean, that describes acceleration anyway, doesn't it? Meters per second squared. Okay. Okay, so if you let the clock roll forward, let's say you're grabbing this guy's speed. Maybe he starts from rest. Right? After 1 second, he's picked up to, well, maybe almost 1 meter per second. After another second, he's going twice as fast at 2 meters per second. Right? And then 3, 4, 5, I'm rounding a little bit. That was like 1 meter per second squared. Yeah. Just picking up 1 meter per second every 1,000 seconds, and 1 meter per second spread. All right, you guys get on the sled dog? The dog. All right, so flip over on the back side here. Um, okay. We have about 20 minutes. I want to make sure I get some of these Atwoods in. So, yeah, you don't only ask a couple of Atwoods. There's an incline question here, so that's kind of interesting. But a couple of Atwoods. I do want to set up my own Atwood, like a really basic fundamental example, and then maybe we'll look at the book questions later. Right, so I'm going to make up my own Atwood right here. My own Atwood. And so I got one of these pulleys right here, one of these pulleys. And maybe I got some lab masses. And I'll connect them with the string over the pulley, and then I'll hold the pulley in place. Okay, just like that. So let's have one mass there, another mass here. Let's call this mass B is how about 5.0 kilograms. Yeah. And over here I'll have mass A as how about 4.0 kilograms. Okay. Now you guys have been doing this Atwood lab for the last couple of days. So let's see, these are kind of close to each other, right? 4 kilograms, 5 kilograms. I think this would probably accelerate slowly enough that you could time this with a stopwatch and then calculate kinematically how much it's accelerating. But we're going to solve this through dynamics. How much should this be accelerating according to Newton's second law of motion? Newton's second law. Right. Now, there are two main different ways to solve this, and they're both kind of on this poster. Right, so I'll walk you guys through verbally the two different ways to set this up and solve this, and then we'll pick one and go with it. Right? So in this pink box is Newton's second law of motion. It tells you how much anything will accelerate. It's net force divided by total matter. Newton's second law. Okay? Now, one way to solve this is what's called a whole systems approach, which is to treat these two weights as external forces, and look, they're fighting each other. This one says, let's go clockwise. This says, no, let's go counterclockwise. Isn't it like tug of war? Okay. So you can subtract the two weight from each other, and that could represent the net force from a whole system point of view. And the total inertia being moved around is the sum of the masses. So it's difference of weights over sum of masses. Hey, this gold box right here, that is the answer to your classic Atwood lab, isn't it? That's exactly what you guys wrote. Okay, right? So we could just jump straight to that and get the answer. Now, something kind of funny about that. You guys notice that I haven't even mentioned the tension in the string yet? Because the tension is just internal to the system. It's just holding it together. Right? Really, these two weights are the driving forces. Yeah. Let me pause this and grab that. All right, back here. All right. So you could, after you figure out the acceleration from a whole system approach, you could go to either one of these green boxes, which is just focused on either mass 1 by itself or mass 2 by itself, and solve for the tension, which is up here, right? Or alternatively, you could have actually started with these two green boxes. So what do these green boxes say? This top green box is only from the perspective of block 1 and only block 1. It says, well, it's got one tension pulling one way, it's got its weight pulling the other way, and that could be the net force just on block 1 that's causing it to maybe accelerate upward. And then this other green box is just from the perspective of block 2 only. It says, well, it's got a weight pulling down, it's got this tension up, and that results in block 2 accelerating down. You could take these two green boxes in a system of equations, say, well, see, I don't from the outset know what is the tension, strain, or the acceleration. Because if you have two equations and two unknowns, can you solve the two unknowns? Yeah, you sure can, right? And that's a different way to do it. I usually prefer to do the whole system approach, so I'm going to jump in straight to the whole system approach. Okay. In fact, I'll spell that out even. I'll say a whole system approach. Okay. I'll go ahead and label some forces here, okay, and then we'll figure out what. Okay, so what's the okay. Maybe we're answering these questions. Okay, what is the acceleration? You might say, like, what's the downward acceleration of a large block? What's the upward acceleration of a small block? It's the same acceleration. Okay? Later on, we can say, what is the tension in the string? Okay? And we can even come up with a kinematic connection, like how far has each block moved. After like some time interval. How about 2.0 seconds? Just to make up a time interval. Maybe it's a really long string and like attaches to the ceiling. How far would it move after 2 seconds? So we can answer all those questions probably in that order. So let's try that. What's the acceleration? So Newton's second law, acceleration is net force on total mass. Like how much something accelerates. Let's do a free body diagram here. FBD, free body diagram. So it's what is the weight of this block pulling straight down? How many newtons? It's a 5 kilogram mass and Earth gravity. That 50 newtons right there. Okay. Now what about this block over here? This is how much weight?
40.
Yeah, 40 newtons. 40 newtons. Okay. So 5 kilograms per kilograms, that weighs 50 newtons or 40 newtons. Right. Now, do you guys see how I made these vectors different lengths? Right, so 50 newtons is longer than 40 newtons. Okay. If I finish the diagram for each block, is there also a tension force? I'll call it F sub T for tension force. And guys, is it exactly the same tension force acting on this other block? F sub T? Okay. That should be true as long as this pulley right here is massless and frictionless, or if it has negligible mass and friction, or one or the other. Okay. This one string can only have one tension in it. Okay. And do you guys notice that there's overall a net force downward on the large block and overall a net force upward on the small block? So this whole thing accelerates like clockwise. Is that okay? Here, compare here. Right, this tension. The other. Same thing. Okay. This tension should be larger than the small weight. Oh, it sure is. Look at that. It's larger than the small weight. And it should also be smaller than the large weight. Oh yeah. Oh yeah. Sure is. Look at that. You guys see how it's all lining up like that? Okay. All right, so back to our Newton's second law right here. Say the acceleration is, well, remember the external forces are the ones that matter, and there's two of them. So these two guys are playing tug of war. So guys, what is the net force? Who can tell me? What's the net force?
90.
Okay, well, they're playing tug of war, right? So would it be 50 newtons minus 40 newtons? Okay. Okay. Now, if you're thinking about, wait, aren't they both pulling down or something like that? Should it be like 90 or something? Or that might be sort of addressing the question of like, if you were holding them here, like what would the tension in this string be if you were holding the whole thing from rest, like starting from rest, right, before they start accelerating, okay? But in this case, if it's clockwise versus counterclockwise, then I have to subtract. Okay? Do you guys remember that too? Like, what if these two happen to be the same weight? What if you put on these two and you let go? Didn't it not even move at all? Because they zeroed out, because there was zero net force from that point of view. Okay. All right, so back over here, guys, what's the total inertia being moved around? What's the total mass? 9 kilograms. Yeah. Isn't it 4 plus 1? So 5 kilograms plus 4 kilograms. And the mass will always add up because mass is a scalar. It's just like what's the total amount? Okay. So the acceleration then is 10 newtons acting on 9 kilograms. Whatever that divides out, 10 on 9. That's like 1.11 meter per second squared. Right. Yeah, there's the first question. Tick off the first answer. Right. This whole thing will pick up at 1.11 meter per second squared. Right. You guys good? Right. So I had a couple of follow-up questions. I was like, I wonder what is the tension in the string? So let's do that one next. Tension in the string. Now the tension in the string, you can either pick block 1 or block 2, like block A or block B, and it'll give you the same tension. Let's do both of those, and I'll show you guys that that is in fact the same. So if you just focus on, say, block A, right, and I'll set just an equation for block A, go like this. So F net equals mass A times the acceleration of block A. And this is on block A, right? So for the net force, wouldn't this be the tension pulling up minus its weight pulling down? Is that true? Okay, so the tension up, which we're solving for right now, minus its weight down, results in mass A accelerating its own amount. Okay, and we know all these other values. Here, I'll just plug them in right now. So I know mass A was 4 kilograms. That goes right here, 4 kg. And Earth gravity, 10 meter per second squared. That results in mass A, which is again 4 kilograms. Accelerating at and we just found this number. Guess what number goes right here? 1.11 meter per second squared. That's everything you need. Okay? Then all I have to do is add this bit right over here. So the tension force would be, say, 4 times 1.11 plus 4 times 10. That looks like 44.4 newtons. Okay, that's the tension force. Okay, does that seem about reasonable? Go back to my diagram. Remember, the small block weighs 40 newtons. I know overall it's gonna kind of drift upwards and accelerate upwards. Yeah, it's being pulled up to 44, pulled down 40. I think that checks out. That makes about sense right there. Okay. Let's do this from the perspective of block B, and I guarantee you we're going to get exactly the same tension force. So from the perspective of this other block, block B, I'll do F net on block B is results in mass B accelerating. Okay. So net force on block B. Now here I'm going to call down positive now because it's over. There's more down than up. Okay. So that's its weight pulling down. So mass B times gravity field minus the tension pulling back. And I'm going to solve tension from scratch. Make you believe I don't really know, but you know what it's got to be. Results in mass B accelerating. Okay. And now we know all these values. So mass B, I told you guys, was 5 kilograms. That was given. Okay. Earth gravity at 10 meter per second squared. Minus the tension we're solving for again. Results in mass B at 5 kilograms. Accelerating at 1.11 meter per second squared. Right. That's okay, right? That's it. Okay. Right. So add over tension, subtract over that. Ft equals, we're throwing in the middle step. It should be that minus that. 50 newtons minus, okay. 5 times 1.11 would be 5.55. That'd be meter per second squared. Oh, sorry, newtons. Whoops, they're all newtons. So tension force is, so if I take my 50 newton weight minus 5 times 1.11, yeah, right there, 44.4, and that's also newtons. Oh yeah, okay. Exact same thing I got by just focusing on block A. Now focus on block B, it's the same tension. Okay, I'll tell you guys all along, there's only one tension in that string, and we just proved it. 44, same force. Is it? Now, I did have one more follow-up question, which is a kinematic connection. How far does the block move in 2 seconds? How far in some time interval? It's how far something moves in some time interval. That's a job for which one of these three amigos? First one. Yeah. Here's how far is a function of time. That's the only one that addresses that. Yeah. How far is a function of time? Guys, could I reasonably assume this starts from rest? That's a reasonable assumption, right? So we're down to x equals 1/2 at squared. Hey, that's the college equation. College. Oh yeah, college. College equation. We're getting some college equation here. So how far something moves boils down to 1/2 at squared. Okay. So we want to know how far it moves. That's x. Okay, so I plug in the full rate of gravity here. What number goes right here? 1.11 meter per second squared. And I said for 2 seconds. So let's plug in 2 seconds. So okay. Don't forget to square the time. Did we get the same thing here? What's 1/2 times a times t squared? I'm getting 2.22 meters. Okay. Yeah, so maybe the string was really long. Looks like 222 centimeters in those 2 seconds. Right. Guys, good. Right. So let's go back to you guys' book puzzles then. Okay. Right, the very last one I think is a classic Atwood setup. So maybe we'll look at that. An Atwood machine used in a stage production to make an actress appear to fly up and out of view of the audience. On like a Peter Pan or something. The system consists of a 52 kilogram actress and a 58 kilogram sandbag connected via a rope over a pulley. Yep, that's an Atwood. the sandbag is released from rest. Determine the magnitude of acceleration for both the actress and the sandbag. Of course, they have the same magnitude, just the sandbag's going down, the actress is flying up. Assume the rope and pulley are massless. Yeah, so let's draw that out. 79. Right, so got some actress here. So, actress, right, she's tied a harness. And then, let's see. Got sandbag up here. Oops. Something like that. All right, I think that's a picture. Right. She has a mass of 52 kilograms, and the sandbag has a mass of 58 kilograms. Right? And all I asked was, what's the acceleration? That's it. So, it's how much does the sandbag weigh? 580 newtons. Okay. How much does she weigh? 520 newtons, right? As long as gravity field is 10 meters per second squared, it's pretty true, right? There's also a tension in the connecting rope. They didn't ask for that, right? And we're not have time to chase that down, but you guys know that's there, that tension force there. Okay, so I can solve this from a whole system approach, right? Just like I started the last one, right? And I can look at these two weights and these two masses and put them all into Newton's second law of motion. So going to Newton's second law of motion, which says that the resulting acceleration is going to be the net force acting on the total mass. And from a whole system approach, these two weights are playing tug of war. Right? The sandbag says, let's go clockwise. And the actor says, no, let's go counterclockwise. Right? Sandbag's going to win. More weight. Right? Up goes the actress. Right? Goes like that. And so the acceleration then is what do we put in the numerator right here? 580 newtons. Then what? Minus 520 newtons. Wouldn't that be the net force? 60 newtons net force. Okay. Acting on, what do we put in the denominator? These two masses right here. So 58 kilograms sandbag plus 52 kilograms actress. Right? That is the total inertia that we moved around by that net force. So the acceleration is, I have 16 newtons net force. What's that, 110 kilograms, I think, is being moved around by that net force. All right, so 60 on 110. Okay. So I'm getting the acceleration is 0.55, it rounds to, meters per second squared. Ooh, pretty good, pretty good. We have 3 minutes, so I have a follow-up question in that case. You guys heard this so far? Okay. So my next question is, suppose this she goes out of view. Maybe out of view is like, let's say 2 meters up. Okay. So how much time to rise 2 meters? Let's say once she goes at 2 meters, she's out of view of the audience, maybe behind a curtain or something. So I think we're back to that first kinematic formula, right? And so we go x equals 1/2 at squared. Okay, let's plug in the numbers first. So right here, put in 2 meters. 1/2. The acceleration we just found right here is 0.55 meters per second squared. 0.55 meters per second squared. Can you solve for time? Now, being squared, so don't forget that. So times 2, divided by acceleration, take the square root. So the last step is to take square root. We got this 2 times this 2. 2 meters. And then divide by here, 0.55 here, 2. Okay, so I did skip a couple of algebra steps because I want to beat the bell, but it does work out like that. So square root 2h on a. Okay. So it looks like, oh, okay. Looks like, is that right? Oh, okay. Whoops, I missed the decimal. And it looks something look off. Okay, yeah, that looks a lot more reasonable. It's like, wait, that didn't look right. Okay. Yeah, 2.7 seconds. 2.7 seconds. Okay, that looks a lot more reasonable. So after about 2.5, 3 seconds, now the actress is out of view. All right, that is our pause point to the day.